So previously, from the beginning of this session, we've been talking about introduction to physics and physical quantities. And we talked about the definition of physics, saying that physics is the study of matter and energy and how they interact with one another. Then we said that um, it is the foundation for engineering and sciences, and it is usually explained using laws and principles. Next, we also talked about the different types of energy: thermal, radiant, light, chemical, nuclear, electrical, gravitational, and mechanical energy. We did some explanations about these types of energy, and then we moved on to states of matter. Talked about solid, liquids, and gases, and we explained how they differ from one another, how solid differs from liquid by being rigid and having a fixed shape and volume, while liquid just is not rigid but has a fixed volume and no definite shape. Gas is being non-rigid, no fixed shape, and also no fixed volume. Then we went into quantities. We talked about physical quantities and the types of physical quantities, which are fundamental and derived quantities. And we talked about units, saying that units are what are used to express quantities. So we explained the types of quantities as fundamental and derived, saying that fundamental is like the bedrock of other quantities, while any other quantity that is not fundamental is a derived quantity, which is a derived quantity and is gotten from talking about units and saying that there are different systems of units. While there are different systems of units, we focus more on the SI units when we come to physics. And this kind of unit measures length in meters, measures mass in kilogram, and also measures time in second. So usually the basic fundamental quantities that are used for that are always made reference to is mass, length, and time. So these mass, length, and time are what are used to carry out dimensional analysis. So we talked about the conversions from different units, saying that um, saying that the conversion of different units is done because of the fact that there are some standard values that can be used to convert these units from one form to another. So we went into dimensional analysis before the break, and I was explaining that dimensional analysis is used to determine whether an equation or an expression is correct. And we gave some examples and tried to see whether we could explain how this dimensional analysis can be used or how we can express different quantities in dimensional form. So we talked about how velocity can be represented as L over T being distance over time, distance being length, sorry, displacement over time, with displacement being length and time being time. So for dimension, before we went on the break, I was explaining that to get the dimension of any quantity, we'll be trying to represent um, the quantity in terms of fundamental quantities. That's the basic fundamental quantities, which are mass, length, and time. So that's how we use to get the dimensions of any quantity. We try to express them or we take them back to their mass, length, and time representation. So that's what I was explaining in the last session. Then we talked about how dimensional analysis can be applied and it is used for checking the validity of equations, in deriving relationships between physical quantities, and also in converting between unit systems. So we're about starting examples before we went on the break. And I said, resuming this break, we'll be starting by asking questions. So I just had to do this quick recap for persons that were not present and are just joining us for the first time. So if you have any question, I would like you to um, speak up. We'll let one person just speak up from the audience. If you have a question, just turn on your mic and ask your question. Is there any question or should we continue?
Question.
Can you guys hear me?
Let's continue, sir.
Okay, you have a question. Okay, go on.
We don't have any question. Let's continue.
Sorry, are you saying you have a question or you don't have any
No,
question?
we don't have any question, sir. We don't have any question.
How can they derive fundamental quantity?
Okay.
Yeah. Ask the question, how can we
So how
derive
can we derive
fundamental quantity?
fundamental quantity?
Okay, how can we define fundamental quantities, right?
How can we
Define.
derive?
Okay, okay. As the name implies, fundamental quantities, they are like the building block. It's just like as if you're, let me clarify also on the definition of fundamental quantities. Probably it would answer your question. Um, we have word. When we were growing up, we were taught alphabets. Then after we were being taught alphabets, then we started learning to make up words. So fundamental quantities are just like alphabets. So they are the startups. They are like the beginning. So A is a letter. You cannot spell A. B is a letter. You cannot spell B. You cannot B from the sound, but B descriptively, like representing it on paper, it is represented with other letter. B is just a letter B. A is just a letter A. It cannot be broken down further. C is just a letter C. It cannot be broken down further. However, the word, let's say end, END, is a combination of three letters, E, N, and D. So this kind of quantity that is a combination of different letters is called a derived quantity. So it's only derived quantities that can be broken down or that can be derived. Fundamental quantities cannot be derived. They are like the starting point. There is no back. There is no going down from them. They are just like the beginning. I don't know whether I answered your question.
Yes, sir.
Okay, thank you. Sorry. Does anyone have another question before we? Does anyone have another question before we continue? Does anyone have another question before we continue?
Good evening, sir.
Okay, good evening.
Yeah, the other time when you were showing slides of prefix, I mean, you showed 10 raised to power minus 2 as deca, then 10 raised to power minus 3 as milli. Oh, sorry, 10 raised to power minus 2 as deci. Which one is deca? Which one is for raised to power minus 1 and raised to power 1? And the other one above raised 1, that's minus 1, yeah. Minus 1, 1, and minus 2, yeah, sorry.
Yeah, you can hear me now, right? Hello, you can hear me?
Yes, yes, sir, yes, sir.
Okay. So Bessie is stepping downward towards the negative direction, while Deca is stepping upwards. Stepping upwards. Deca is when you'd have times 10 to the power of 1. Decameter, there is decameter, there is hectometer. Those ones are moving upwards. We have kilometer and so on. That's how you move upwards. But coming downwards is when you have deci, cent, there is decimeter. Though both of them are represented with DM, DM. Decameter is usually represented with capital D, then small letter m, while decimeter is represented with small d, then small m. So after this session of teaching, we'll be taking the final question and answer session. So let's go before we go into the first example, because this example now in this next session is about dimensional analysis. So we talked about dimensional analysis and saying that to get the dimension of any quantity, you'll be trying to express it in form of fundamental quantities, that's in form of mass, length, and time. So and we said that this can be used to determine whether an equation is correct. So we'll be seeing how we can use it to check whether equation is correct. We'll also be seeing how we can use dimensional analysis to also derive the relationship between physical quantities. And we will also see how it can be used to convert between different unit systems, that is from CGS to SI units and so on. So let's go. Example one, it says check if the equation V is equal to U plus AT is dimensionally correct. So in this question, we're trying to find if an equation is dimensionally correct. So for an equation to be dimensionally correct, it means the dimension of things on the right-hand side of the equal to sign must be the same with the dimension of things on the left-hand side of the equal to sign. So I'll be repeating myself in case of those that will be writing down. To check whether an equation is dimensionally correct, you will check the dimension of every of the quantity on the right hand side and also check the dimension of every of the quantity on the left hand side. If the quantity on the left hand side, the dimension of the quantity on the left hand side is equal to the dimension of the quantity on the right hand side, you can say that that equation is dimensionally correct. So now let's see how we could try that for this example. Let's see how we can try that for this example. So for this example, we have the equation V is equal to U plus AT. So on our left-hand side, we have just V on our left-hand side. Then on our right-hand side, we have U plus AT. So first off, before we start solving for this problem, when we have letters like, sorry, when we have signs, mathematical signs like plus, minus, separating two parameters or two numbers in different alphabets, it means that you've kind of created a unique quantity. Let me break what I'm talking about down. Let me see whether I can use this. So now we have V is equal to U plus AT, right? So
Yeah.
with that, there's a plus sign. There's a plus sign separating U and AT. So this means that U on its own will be treated as an independent unit. AT that together we will treat it as another independent unit. So as mean we had another letter, maybe like plus D. D also will be treated as an independent unit. You get? I hope you are following, Sha. So when we have signs like plus or minus separating different units or different groups of units, those group of units will be treated as a single unit or an independent unit. So like in this case now we have um, V is our left hand side and everything here is our right hand side. But now on this our right hand side, we then have splittings where the plus sign is splitting the right hand side. We have this plus sign dividing this U and AT. We have another plus sign that I just created dividing AT and D. So each of these ones on the right hand side, U will be treated as an independent unit. AT will be treated as an independent unit. D will be treated as an independent unit. Though we know that I'm going to add this D now. So you would see why I'm giving this explanation. So let's move on to seeing how this would imply. So V now is one unit on our on our left hand side. V is the expression for our left hand side. Expression for our left hand side. Then we have U plus AT as the expression for our right hand side. So, but on this expression for our right hand side, they are divided into two independent units, U and AT. So what this implies, this left hand side, if this same thing happen on the left hand side, you will still do the same thing. If there's a plus sign dividing the left and right hand side, or dividing the parameters on the left hand side, you will still do the same thing. So let me quit talking or speaking many words. You will check the dimension of what is on the left hand side and also check the dimension of what is on the right hand side. But once there's a plus, it's like a breaker where it will break these things on the right hand side into independent units. So what is on the left hand side must be equal to this side, this independent side, as this independent side, and must also be equal to this independent side. I don't know whether it's correct. I don't know whether you understand what I mean. When you have an expression where on the left hand side or on the right hand side, there are different parameters or group of parameters that are separated by plus or minus sign. Because of that plus or minus sign, those entities will be treated independently and they must be equal to what is on the right hand side or on the left hand side. So let's see what I mean by all this I'm explaining. So we have our v representing final velocity. We have our u representing initial velocity, a representing acceleration, and t representing time. So as I was saying, our left hand side is v. Our left hand side is v. But we'll be getting the dimensions for each of these expressions first. We'll be getting their dimensions first. So in step one, as I was saying, the first thing we'll do is to get the dimension of the parameters. We'll get the dimension of each of the parameters present. So we have velocity v. The dimension for v is L t raised power minus 1. Dimension for u is the same thing with v because both of them are velocity. So it's same as Lt raised power minus 1. Then the dimension for acceleration. Acceleration is velocity over time. That is Lt raised power minus 1 raised power minus 1 divided by time. So that would making it Lt raised power minus 2. So that's dimension for acceleration, Lt raised power minus 2. It's a constant dimension. Acceleration would always be Lt raised power minus 2. Then time is always t, because time is t. Time is always t. So these are the dimensions for v, u, a, and t. And that's what we have from our question here, v, u, a, and t. So with this, we've done our first step, getting the dimension of all the parameters that were given to us. So the next step now is, after we've gotten this dimension, is now to represent them in form of right-hand side and left-hand side. We'll group them into the right-hand side and left-hand side. And as I was explaining earlier, I said the right-hand side must be equal to the left-hand side for an expression to be dimensionally correct. So let's see how that would happen. Let's see how that will happen. So the second step is to analyze the right-hand side. And as I was explaining earlier, I said, I don't know whether you guys were still hearing me at that point, where I said, once you have a positive sign, splitting two parameters or two letters, you will treat the two letters independently. That is, you get the dimension of one of the letter and it must be equal to the dimension of the second letter on that same side. So meaning that the dimension of u should be equal to the combined dimension of a and t. What do I mean by that? We have our u. Our u was equal to L T raised power minus 1. And our A was equal to L T raised power minus 2. LT raised power minus 2. Then our T is, this is times our T is T. So if we check this our AT is the dimension of A multiplied by the dimension of T. And from indices, we know that T raised power minus 2 times T is the same thing as is going to reduce the number of T on the bigger side, that is on the minus side. This is the same as saying T raised power minus 2 plus 1. When you have T raised power minus 2 times T raised power 1, the same as T raised power minus 2 plus 1. And that will be giving us LT, that is our AT now will be, our AT, combined AT will be equal to LT raised power minus 1. So from here we can see that our AT is equal to LT raised power minus 1. Our U is equal to LT raised power minus 1. So now if we go to our right hand side, on our left hand side rather, our V here was also LT raised power minus 1. So since everything on our left hand side is equal to everything on our right hand side, we can say that this equation is dimensionally correct. I don't know if you are hearing me or if you guys are following me.
Yes, sir.
The first, the first step to check for dimensional correction is, or to check whether an equation is dimensionally correct, you would first express all the parameters in form of dimension. Then you will check those ones that are grouped together. The second step is to check those ones that are grouped together on the right hand side. Check them individually in form of their individual groups, separating them by plus and minus sign. If there's a plus sign separating two alphabets or two or more alphabets, you take those alphabets that are grouped together, get the dimension, their combined dimension, and check if their combined dimension on the right hand side, or the combined dimension on the right hand side is equal to all the combined direction on the left hand side. You can say that that equation is dimensionally correct. So that's for checking whether an equation is dimensionally correct. So for the sake of time, let's move on um, to the next application of dimensional analysis. The second application is to derive relationships between physical quantities. That is to derive the relationship between physical quantities. So for this example, we'll be using the formula for force. So in this, for what it means to derive the relationship for for physical quantities, what it means is for some expression where you have like for some equations, you have some equations like S is equal to UT plus half AT squared. That T squared, it has mean you did not know whether it is T squared or it is T cube or something like that. You could use dimensional analysis to determine the power on each of the parameters present in an equation or in an expression. So that's what this expression is trying to talk about. So for this example now, we'll be using the general Newton's law that states that F is equal to mass times acceleration. So now we are going to be assuming we don't know whether F, F is equal to m raised power 1 or F is equal to m raised power 2, a raised power 2. We'll be assuming we don't know the powers of m and a in this case. So we'll be seeing how we can use dimensional analysis to determine the powers of the parameters in this equation. So the equation now is F is directly proportional to m raised power a times a raised power b, where we are looking for the values of a and b, trying to know what a and b are. So we'll see how we'll use dimensional analysis to get this expression. So first, the same thing would always be to get the dimension of each of the parameters individually. So sorry, for this one, we would get the dimension for a we get dimension for F, we get dimension for F, get dimension for M, and we get dimension of for A. That's from this expression here. We get dimension of each of the parameters F, M, and A. So force, the dimension for force is usually kilogram meters per second. The unit for force is kilogram meter over second squared. Over second squared. Kilogram meters over second squared. So from the unit of force, we can get the dimension for force. Sorry. From unit of force, we can get the dimension of force. So kilogram is for M. Kilogram is M. Meter is L. And over time is S. Sorry, time is T. Like seconds is T. That is T squared. So with that, we've been able to get the dimension for force. The dimension for force would now be ml all over T squared, as you can see on this side. As you can see on this side, this point, this is dimension for force. Then also the dimension for mass is meter, and dimension for acceleration, as we did earlier, is LT raised power minus 2. So now we've gotten the individual dimension. The first step is done. So after getting these individual dimensions for every parameter present, the next thing you do is to set up the dimensional equation. That's this expression we had here. This is our expression we had here, where we had f directly proportional to m raised power a times a raised power b. We'll then use this thing now as our f. We'll replace it as our f. We'll use m and replace as our m here, raised power a, and we'll use lt raised power minus 2 to replace our a on this side here to be lt raised power t squared. Sorry, lt raised power minus 2 b. Let me write what I'm saying down. Let me write what I'm saying down here. Our f, instead of writing f, we'll be writing it as m l t raised power minus 2 equals to m on this side here. We are using this equation. M here is raised power a, so we have m raised power a. Then a on this side is this. This is what our a is, lt raised power minus 2. So our a is lt raised power minus 2, so it will be times lt raised power minus 2. Then you put it all in brackets and put this our b, alphabet b here. So with that, we've gotten the single expression that is equal to this. So from this expression now, we'll try to find the values of a and b. There's values of this a here and the value of this b here. So that's what we'll be doing in the next slide. Let's move on and see how it happens. So that expression I gave in the previous slide is what we have up here. Everything I did in the previous slide is what we have up here. M for this one representing F, this one representing M, and this one representing A, then raise power, the powers that are there. So then now with this now, we'll then simplify this or get using indices. We'll group all the M's together and all the T's together. So we'll use this right-hand side. We'll keep everything on the left-hand side aside and use everything on the right-hand side and put them in form of indical expression. So for M, we have M here, M raised power A. Here we have, if we open these brackets, here, we have L times the LB. We have LB. First we have MA. Then next we have times our L here, it's LB because B is LT squared is inside the bracket of B. So we have LB. Then we have t raised power minus 2b, because t raised power minus 2 is also in the same bracket with um b. So we are having t raised power minus 2b. So that's what we have as this expression here. So with that expression now, we would then compare the right hand side with the left hand side by matching their powers. So what we have here on this our right hand side is this up here. This is what we have on our right hand side here. The power of m is a. So, but on the left hand side, the power of m on the left hand side, power of m on the left hand side, that is here. The power of m will compare it to the power of m in this portion. We compare the power of m on the red circle with the power of m on the yellow circle. Sorry, on the yellow circle. The power of m in the red circle is 1. So that's why they said a is equal to 1, because the power of m in the yellow circle is a, power of m in the red circle is 1. So it is, you will say that the power of m generally can be said to be equal to 1. So for L now, we need the power of L on in the red circle is 1, while the power of L in the blue circle is B. So we can say that B is equal to 1. Comparing right hand side with left hand side, the powers. So we can say that our B is equal to 1. So for our T now, the power of T on the red cycle is T raised power minus 2, while the power of T in our yellow cycle is T raised power minus 2b. So we can say that minus 2 is equal to minus 2b. And that's what we had here. We're making B subject of formula. We'll be having that our B will then be equal to minus 1. So we can say that the power of B is 1 and the power of A is also 1. Then putting it in the first equation we had, we'll then be having that the first equation is going to be equal to F equals to M A. So now the next portion we'll be going into is converting between systems of unit, or converting between two unit systems. So this is where we'll be converting from CGS unit to SI unit, or from any other type of unit to SI unit, or just switching between different systems of units. So this is one thing that also dimensional analysis can be used for. So actually, this is common. We probably are used to converting from kilogram to gram, from kilometer to meter. But in some cases, in some questions, in exam cases, you would see some expressions where you'd have kilogram over meter, and you're expected to convert it to maybe gram per meter, and it will be confusing because of the whole thing would start getting kind of confusing. Some of them might even be more complex than that. So I'll be giving a simple way that we could use to memorize how we can convert from different systems of units to another system of units. So first, the thing you would first need to know is if that's the current system of units, that the expression you are giving, if it's in a if the unit is in the larger state, if it's in the larger form, like we know that kilogram and gram, kilogram is bigger than gram. So we would compare if the unit we are at is bigger than the unit we are going to. We would use the value, the conversion value on the smaller one to multiply the value of the bigger one. So let me explain what I mean by that. We know that 1000 gram is equal to 1 kilogram. We know that kilogram is bigger than gram. So with this knowledge now, if you are converting from kilogram to gram, you will take this factor behind gram being the smaller one and multiply it by whatsoever you have as your kilogram. So if you have something like 2 kilogram, you would multiply that 2 by 1000 and you'll be able to get the value in gram. You'll be able to get the value in gram. So in simple terms, I'm trying to simplify it is when you have the small unit and you have the bigger unit, and you're trying to convert from bigger units to when you're trying to convert from bigger unit to smaller unit, you take the fraction that is behind the smaller unit and multiply by the fraction on the bigger unit to get the conversion into the smaller unit. That is, if you are changing from gram to kilogram, the first thing you will do is between gram and kilogram, which one is bigger? Once you found out the one that is bigger, you then check, okay, am I moving from the smallest to biggest or from the biggest to the smallest? If you're moving from smallest to biggest, you will divide by the conversion factor. But if you're moving from biggest to smallest, you would multiply by the conversion factor. I think that's the simplest way I think I should put it. When you're moving from a smaller unit to a bigger unit, you divide by the conversion factor. But when you're moving from a bigger unit to a smaller unit, you would multiply by the conversion factor. So there is actually a twist when the bigger unit is in an expression where the unit is something like when the unit is something like kilometer, where you have kilometer per hour. With the one that is up on this fraction now, kilometer and hour, they are both big units if you are comparing them to SI units. SI unit is meter per second. Sorry, meter per second. So if you were to convert from kilometer per hour to meter per second, on this, the ones up on this fraction, kilometer to meter, it's straightforward. We are converting from a bigger unit to a smaller unit. So you multiply by the fraction of conversion, by the conversion factor. So, but now you are on when you have a fraction now, and you have the same thing, bigger to smaller, but the bigger one is the denominator in a fractional unit. Instead of multiplying, you will divide. In the case when you don't have it as a fraction and the bigger unit is not under, you will do the normal from big to small, you multiply, from small to big, you divide. But when it is now under a fraction, when the bigger unit is under in a fractional expression, from big to small will no more be multiplication. It will now be from big to small will then be division, while from small to big will become multiplication. So let's see these things I'm saying. Let's see how it applies. We have a question where they say we are changing from 90 kilometer per hour to meters per second. So how I convert this kind of expression is I would first convert from this one up to this one up. I'll compare the one. So what I do, so what I do is first, I always try to convert the ones up. When you have a fractional unit and you're trying to convert from one fractional unit to another fractional unit. What I first do is I check the ones up, then check the ones bigger, I would multiply with these fractions of the smaller units with the fraction of conversion. Once I'm done with that, I'll then move to the ones down and do the reverse for it. So in this case now, if I wanted to convert from 90 kilometer per hour to meter per second, the first thing I'll do is from kilometer to meter, it is 1000. So first I would do this kilometer to meter first. I will multiply 90 by 1 to second. It is also from big to small. It's also from big to small. But now because hour is under in this fractional expression, I will then divide from hour to second. We have 60 seconds make 1 minute, 60 minutes make 1 hour. That is 60 times 60. Normally, 60 times 60 is 3600. If this hour was up on this fraction, we would multiply the 90 by 60,000 by 3600. But because hour is under now, we will divide it by 3,600 because we're moving from hour to second. So now the conversion expression will now be 90 times 1,000 all over 3,600. So that's what we'll do in this case. That's what we'll do in this case. We'll convert it using that form of conversion. 90 times 1,000 divided by 3,600. That's what we had here. That's what we had. So simply putting, when you're moving from smaller to bigger units, you would divide. When you're moving from bigger units to smaller units, you would multiply. You multiply. So this case would be reversed when you found the position of the bigger unit or the smaller unit. If the position of bigger unit is as a numerator, that is up on a fractional expression, you would obey this rule. But when the position of the bigger unit or smaller unit is as a denominator in a fractional expression, you would reverse this rule that we talked about here. So that's just the simple way I think is we could use to convert from different units, especially units that have fractional expressions. So doing that, we would have our final answer to be 25 seconds when we multiply 90 times 1,000, dividing them by 3,600. We will then have our final answer to be 25 meters per second. So let's move on to the next error analysis. But before we go to error analysis, I don't know, let me stop here and ask for anyone that has questions. Does anyone have any question?
Yeah, please ask question. When you talked about that one equating checking of correctness of an equation,
Yeah.
please I want to ask m raised to the power 1. Why is m raised to power 1 instead of 0?
Are you referring to this portion or the first example? This one?
Yes, the first example. No,
Okay,
this.
this one.
Yes.
In this example, we did not have M. I think you are referring to this example. This is one that has M.
Yes. This one.
Yeah. So M here. Why M is equal to 1? Why M is raised to power 1 is because anything that you don't see a power, that they did not put a figure as the power, you would always know that there's an invisible one that is above. If you have A, just A, it means it is the same as A raised to power 1. If you have B, it is the same as B raised to power 1. If you have 5, just 5, it's the same as 5 raised to power 1. So that is the reason why you did not just see, I guess I said M is the same as M raised to power 1. I don't know whether you get what I mean.
Yes, I get it. Thank you.
So, any other question? Okay. In absence of question, let me just wrap up with the final portions of these lessons where we have error and error analysis. So errors are stuff that are inevitable. In every calculation we are doing, everything we are doing, there is always a level of error, so long as it's human. Even computers too, they perform tasks with some level of errors. So error, as I defined here, there are differences between the measured value and the true value. So you cannot say that there's an error if you don't know the true value of any particular thing. Someone cannot tell you anything if the person does not have the correct. Someone cannot tell you you are wrong if the person does not know what is wrong. So that's the same thing that happens when it comes to error analysis. You cannot say that there's an error when there is no true value. So by definition, error is the difference between the true value and the measured value. As I stated initially, I said no measurement is perfect. Every measurement, there's always a level of error. So there's always a level of error in every single thing. Some kind of errors, why some are more pronounced. So in this case, we'll be moving to the types of error. We have I listed three types of error. There are still more types of error, but for the sake of this lesson, we'll be talking about just these three types of error. And we have systematic errors, random errors, gross errors. So these are the three types of errors that we'll be talking about in this lesson. So for systematic errors, these are the errors that are as a result of faults from the instruments that we're using to measure. So when the instrument, as when we are using a thermometer to measure temperature, if the thermometer is faulty, that error is not your fault. It's actually the fault from the thermometer that you're using to measure. So this kind of error is known as systematic error. So random error, this is the kind of error that is unpredictable. Usually they are depending on the person that is measuring. Someone that's probably trying to read off a reading from let's assume you are trying to take off a reading from ruler. Someone on the left hand side might be seeing it that it is 5.6. Someone on the right hand side might be seeing that it's 5.5. So this kind of error now, nobody can exactly tell which of them is correct, whether the person on the right hand side has an eye problem or the person on the left hand side has an eye problem. That kind of error, you can already predict it exactly. So this kind of error is called random error. It's error that can happen generally. It can happen to anybody because depending on your angle, different things can cause this kind of random error. So this is the kind of error that is unpredictable. So we then have gross error, which is the error that occurs as a result of mistakes from readings or calculation. So assuming now you were trying to calculate, maybe doing a mathematical expression or doing a mathematical calculation, and you rounded off something. Maybe they gave you a value. They said the answer is 3.142. And you're supposed to use that value 3.142 in another place. Then you rounded it up to 3.1 and you are solving, you get your final answer. Maybe your final answer is giving you 10. Someone else, the final answer is giving 9.7. This kind of error is kind of error they call gross error. Is usually type of error is gotten as a result of approximation or adjustment of readings during calculation. So these are the three types of errors that are more pronounced when you are talking about errors. So as we're talking about gross errors, we mentioned stuffs about rounding off. So basically, I'm sure everyone here is aware of rounding off or conversion from two significant figure, three significant figure, decimal place. These are forms of estimations where you could round up or round down. So from the course content under this week, we are meant to talk about significant figures. So this will just be like a reminder to us because I believe that most persons already know what significant figure or how to round off to significant figures. But I'll just go through it because it's part of the scheme. So significant figure, this is I don't know if I would give it, you would not really ask you for definition for significant figure, but I would explain what significant figure means. They're actually a form of rounding off where you would observe the 5 number, the number that has the, assuming you are trying to round up to 3 significant figure, you would count 3 figures. Then if the third figure, the figure after the third figure has a value that is greater than 5, you would round it up. You would convert that figure to 1 and add it to the third figure. But if it is less than 1, you would round it down. That is, you would make it 0 and add it to the third figure. So I'm sure this is popular. We know stuff like that. Where you have something like this. You have something like maybe 3 points, 3.145, and you're asked to round it up to 3 significant figure. You will start counting 1, 2, 3. Then the next digit after it, you check, is it up to 5? If it's up to 5, you would round it up. That is, you convert it to 1 and add it to the figure. That's when you're talking about significant figure or 3 significant figure. You add it to this, make it your final answer 3. Rounding off. And so that being said, I think we'll be moving to graphical analysis. So we've talked about error analysis, we've talked about dimensional analysis. Another part we're talking about is graphical analysis. And these are ways that we represent, um, that we examine or we measure quantities in physics. We measure quantities using graphs. Graphs are very common in physics. Either they are line graphs, scatter plots, pie charts, histogram, or whatsoever. There are different types of graphical analysis that are used in physics, both basic physics and advanced level physics. So for basic physics, what we mostly see is just line graph, where they will tell you to draw, maybe they will give you parameters and they'll tell you find the line of best fit or find the slope or find the intersect. So usually these types of analysis are called graphical analysis, where you use pie charts or use different forms of charts to analyze readings. So there are different types of graphs. We have line graph, bar graph, scatter plots, slope graph, and so on. Sorry, not slope graph. We have scatter plots and so on. So slopes of graph in physics, graphical analysis in physics, especially practical physics, they always ask that you'd find the slope or the gradient of a practical work you've done. When you've represented it in tables or on a graph, you'll be expected to determine the slope of that graph or the gradient of that graph. So the slope of that graph is actually the same thing as the rate of change between the parameter on the y-axis with the parameter on the x-axis. Some people might not already know exactly what y-axis and x-axis mean clearly. X-axis is always going to be the axis that is moving from your left to right. It's always horizontal. While y-axis is one that always moves up from up to down. So y is always the one that moves from up to down, while x is always one that moves from left to right. So this is how we represent graph. Graphs are usually represented in x and y coordinates. And to get the slope of any graph or any line that is drawn on a graph is usually the rate of change of y divided by the rate of change of x. Is usually the rate of change of y divided by the rate of change of x. So this is what it means. When you draw a straight line or you have a straight line graph like this one, the slope, you would may take 2 points on that straight line. Then you check the change on the y-axis, you write it down, and check the change on the x-axis, you write it down. Then you divide the one on the y-axis by the one on the x-axis. So that's how you used to get the slope of any graph. You check the change on the y-axis, dividing it by the change on the x-axis. Then the intercept of any line graph or any line plot is always where that straight line that you drew, where it touched on the y-axis. I'll explain which one is the y-axis. So wherever the straight line that you plotted landed, where it landed or where it intersected on the y-axis is always called your intercept. So in case you've been hearing stuff that saying find the slope of a graph and find the intercept of a graph, they're actually simple terms. It's just the slope is checking the y-axis, mark 2 points on the straight line, any 2 points. Then you check the difference between the 2 points, tracing it to the x and y-axis. Then you check the difference, the distance here to here, check the distance here to here. Then the one on the y-axis, you divide it by the one on the x-axis, and you will get your slope or your gradient. While the intercept is that point where that straight line touches on the y-axis, it does not change. Wherever that straight line touches on the y-axis, is always going to be your intercept. So there's also a mathematical expression that's called the equation of a line, which is given as y equals to mx plus c, where m represents the slope and c represents the intercept. So sometimes you might be asked, after you've gotten the slope of a graph and the intercept, they'll tell you, okay, find the equation of the line. So it just means write y, then equal to whatsoever you got as your slope, put it first, and write x plus whatsoever you get as your intercept, put it next. So that's how they get the equation of any line. Once you can be able to get the intercept of that line and also get the gradient of the line or the slope of the line, you can be able to get the equation of that line. So moving on to the next thing, we have measurements of length, mass, and time. So I know we've seen in some past questions where they talked about caliper, vernier caliper, and micrometer screw gauge. So this is one kind of question that always come out in most exams, both JAMB, WAEC, JUPEB, questions under vernier caliper. If someone is very good on answering this kind of question, I can say you can be able to beat your chest that you will get at least 3 questions out of the whole question that they will give you in your question. If you can get very good in at least vernier caliper and micrometer screw gauge, you can be able to tell yourself that okay, even if they should bring any question at all under physics, I'll be able to answer at least three because usually in the past questions, they try to bring in at least three or at least around 3 questions each year under vernier caliper and micrometer screw gauge. So it will be of importance that you learn all these things that we've been teaching, that I've been trying to teach since the beginning. Because the beauty of this kind of learning is once you've once you've been listening to everything I have been talking about and you've tried to be learning what I've been trying to teach, you are reducing the number of things you don't know in your exams. You are reducing the number of things you don't know because the little one that we've learned here, or we are trying to learn here, is if you really would learn it, it would be subtracting from the ones you have in the exam. Anyone you've learned here now, it should mean that in the exam, if you practice it forward in the exam, any question that should come out of this topic, you should be able to smash that question and at least give yourself some points from the total points. So before we round off for today's class, I'll be explaining more on how to check measurements on vernier caliper and micrometer screw gauge. So above here we have the vernier caliper. It's the one that looks like this, and under we have the micrometer screw gauge. That's this, and this is vernier caliper, while this is the micrometer screw gauge. So to get readings in vernier caliper, it's actually very simple. It's one of the most simple kind of calculation that could come out in physics. But if you don't know it, you just lose a bonus question that you could probably have used to probably get 2 or 3 points. So to get the readings of a caliper or a vernier caliper, there are 2 things you would pay attention to. The 2 things you pay attention to is the main scale and the vernier scale. So the main scale is the reading that is like on the normal ruler. All these readings that are on this are like normal ruler. The ones up, they are known as the main scale. They're known as the main scale. So if you see the main scale, you check what is the reading, what is the gap between the readings on the main scale. Here we have 0, 10, 20, 30, 40. It means that if this is 0 and this is 10, it means that in these small ones now will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The next one now be 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The next will be 21, 22, and so on the main scale. On the main scale. So now to get the reading on the vernier scale, there are 2 things you need to do. You will check where the 0 mark on the vernier scale, where it starts from. You will check the number that is before it. The number that is before it. That is the reading, the main scale reading. So like this, from this our diagram now, we have 0 here. And at this point of 0, before 0, we had this mark here. We had this was the last reading. And if you count it from here, this is 10, 11, this is 10, this is 11, 12, 13, 14, 15. So that was our number 15th reading before the 0 mark. So the 0 mark was here. This was 0 mark here. But the last reading that stopped before it was 15. So the main scale reading is 15. So we'll write it down one side, 15. So then once you've gotten the main scale reading, next thing you do is the vernier scale reading. So on this vernier scale reading, you will check where did the first vernier scale intersect with a reading on the main scale. The vernier scale reading, number one, did not intersect well. Number two, did not intersect well. That is, it did not lap exactly on the main scale reading. Number one did not intersect well. It was almost intersecting, but it did not. Number two did not intersect at all. Number three did not intersect at all. Number four, the same thing, it did not intersect. Number five almost intersected, but it did not intersect. Number six was very close. Number seven was very close. But now number eight was the one that lapped perfectly, like completely with the main scale reading. So this point where it intersected, it was on number eight. So for that reason, it will now be, you would add that eight to the main scale reading on the point side. So you will now be having 15.8 as your total vernier scale reading. You would check the reading on the main scale first by looking at the zero mark of the vernier scale. Once you've gotten it, you then go to the vernier scale and look for which of the vernier scale reading intersected with the main scale reading. So that's how we check vernier scale reading. So I don't know if anyone has any question before I go on to micrometer screw gauge. If you have any question, I would like you to just turn on your mic and ask the question because I think this one is a little bit dicey. So if you have any question, just put your questions immediately.
Yes.
Any question? Okay. So let's.
Excuse me.
Okay,
Is
I'm
it
listening.
that the standard how do I put it? The standard is it SI unit or something? Not like SI unit. I mean the prefix or something of millimeter. Is it millimeter or it can also be in centimeter? It can be in other meter. This blah, blah, blah.
Mhm. Is it? Are you referring to this vernier scale stuff or something else?
Yeah. The vernier scale.
Yeah, it could be in something different. It could be in something different. It could be in millimeter, but usually it is mostly in millimeter. It could be in centimeter, but the main thing is to observe the unit that they gave you on the vernier scale. The unit that they gave you on the vernier scale. So that's what will tell you the unit you will give your final answer. So in this question now, we see on the vernier scale they gave us millimeter. So meaning that our final answer will be in millimeter. If assuming they put it as centimeter, our final answer would have been in centimeter. But usually vernier scales are mostly in millimeter. So is it clear? Or did I
Yes,
answer
yes.
your question?
Mm.
Okay.
Yes, thank you.
So we can move on to micrometer screw gauge. Let's move on for the sake of time. We are far we've gone beyond our time. So let's go to micrometer screw gauge. So it's similar to vernier scale, but there's, I can say micrometer screw gauge is much easier than reading from a vernier scale. So for a micrometer screw gauge, it's almost the same thing. We also have the main scale. The main scale is always the one on this side. This is always the main scale, while the reading that is like this here on this side is known as the vernier scale, or the, not really the vernier side, but you could call it the um, auxiliary scale. So this is the main scale, while this is like the auxiliary scale. So for this micrometer screw gauge, the reading is always similar. We have here on this first side, we have 0. The next one is 1. Or normally, if they had expanded it more, they would have shown you that this is representing 1, this is 2, this is 3, this is 4. Then if this is 0 and this is 1, in between 0 and 1 is 0.5. In between 1 and 2 is 1.5. In between 2 and 3 is 2.5. In between 3 and 4 is 3.5. In between 4 and 5 that we are not seeing will be 4.5. So now that's what this thing is. It's just like 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. So the last reading you see on this main scale is what will be your main scale reading. So the last reading that we could see here was our 4.5 points. So you would write it down as your main scale reading. You write it at the side of your notes, or you just write somewhere 4.5. Let me write it here 4.5. 4.5. So we've gotten our main scale reading. So then we'll then look at our um, auxiliary scale reading now. So it's starting from this bottom going upwards. So we have 15, 20, 25, 30. So it means if this is 15, this small one will be 16, 17, 18, 19, then 20, 21, 22, 23, 24, 25, 26, 27, 28, and so on. So now we would use where this center line of the main scale, where it stopped at, it does not necessarily need to overlap exactly with it, but the one it's blocked, reading from down upwards, the one it stopped is going to be the value that we will take. It's going to be the value that we will take. Such that the reading will then be 4.5. And that reading, since it is 22, it will be 0.22. This reading here is always 0 point, 0 point whatsoever is on this side. 0 point whatsoever is on this side. So now we have 4.5 coming this way. Then we have 0 point something coming this way. So now we counted, this is 20, 21, 22. So it is 0.22. So 0.22 plus 4.5 is going to be giving us 4.72. So the final answer is going to be 4.72 as our micrometer screw gauge reading for this one. For this one. So now let's go to the second example on this same micrometer screw gauge. The second side we have 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4. It stopped at 4. So our main scale reading is 4. Then on this side now, we'll start taking 15, 16, 17, 18, 19, 20, 21, 22. It intersected as 22, so it is 0.22. So because it intersected at 0.22, you add that 0.22 to your main scale reading. That is 4.0 plus 0.22. So our final answer for this case would be 4.22. So that would be our final answer for this micrometer screw gauge. I believe it should be clear. Anybody has a question? Sorry, does anyone have a question on this micrometer screw gauge before we go on? Any question? Okay, I think that there's no question. So when you see a vernier caliper reading, or you see a reading and they are asked to check the to determine the reading that was given, sorry, you're given a vernier scale and you're asked to read the output from that vernier scale. The first thing you would always do is you check the zero mark. You check the zero mark. You check for the zero mark on the vernier scale. That's this zero mark on the vernier scale. Then once you found that zero mark, you check the last number before that zero mark. You check what value that last number is. You write it down as your main scale reading. Then next, you check for this vernier scale reading, where it intersects with the main scale reading. The first place where it intersects with the main scale reading perfectly is going to be your main scale, your vernier scale reading, and you put that 0 point whatsoever that reading is. So then you add it together with giving you 15.8 millimeter. So going to micrometer screw gauge is almost the same, but this one now you check the main scale reading 0, 0.5, 1, 1.5, 2, 2.5, and so on, until you check the last one that you can find on this main scale reading. Once you found it, you then write it down. Then you come to your vernier scale reading, read it upwards, 15, 16, 17, 18. Then whatsoever you get, whatsoever value you get, you put it at 0 point, that reading. Then you add it to your main scale reading and you'll be getting your final answer for that. So that's for this. So in experiments, we usually hear, if we've been doing practical, they'll tell us, okay, oh, what are the precautions that you took when you were carrying out practicals. Major precautions that are expected to be taken are parallax error, avoiding parallax error. That is error that occurs as a result of reading two parallel stuffs, being sure that they are actually parallel and not that they slightly were aside from each other. So try to avoid parallax error. That is error that could come from viewing stuff that are parallel. Then another measurement that you should always avoid, another precaution that you should always take is to repeat measurements to reduce random errors. That is, you try to take whatever measurement you're measuring. You would not just take, maybe you are trying to measure a length, you will not just measure it once. It's giving you 4.7. You say that is the final reading. As you measure the first time and you get 4.7, you measure it again. Probably you might get 4.6. You measure it the third time, you might get 4.7. Then you take the average of those readings. So that's what the second precaution that you are supposed to be taking, usually in physics practical, because most of the times the errors that people always see when they say write errors that you should observe in an experiment, the first thing that everybody remembers is avoid error due to parallax or avoid parallax error. They don't know that there are some other errors that you should avoid. So some other errors is make sure that you took repeated measurements. Make sure you avoid parallax error, and then also appropriate instruments. Use appropriate instruments. So we've gotten to the end of today's session. Sorry for overshooting the time. I don't know if anyone still has another question. I'll be taking just one question if there is any, because I think I've been taking questions since the beginning of the class. So does anyone have any question, or we should call it a day? Okay, no question. And that will be the end of today's lesson. So thank you all for joining.